Okay, let's get started. So hopefully most of you turned in your homework last night. We will start grading that after the deadline, for the late deadline, and that's going to be pretty much how we're going to work during the semester, so 3 days afterwards, and then we'll try to get it back to you within a week. Once the deadline, the late deadline passes, when we don't accept any more homework, solutions will be posted. And those will be up on Courseworks for you to look at it. So if you have any questions and anything like that, come to office hours, ask questions in Campus Wire, that type of stuff. And we'll give you some details about how we're going to give back feedback once we grade the first homework. So there is another homework that just got released. And apparently I labeled it 1. I'm really having a tough time with this numbering thing. Counting doesn't seem to be my strong suit. Or this is homework 2. It's just air is the purpose of it. So this is available to you right now. This is going to be 100 points. The first homework was actually out of 50 points, if you noticed. This one's going to be out of 100. Okay? So again, the first homework was mostly to try to get you acquainted with the notebook, some of the topics and the background that you should have coming into the course, and now we're going to dive into the material of the course. This is going to be due a week from this morning. Okay, so next Monday, 11:59, it will be due. Okay, and that will be more or less the kind of length of time you'll have for each of the homeworks is a week now going forward. So are there any questions before we get started? Yes?
So it's due?
Yes.
And the availability?
That's late days, yes. Yeah, so the availability is you can still turn it in through the deadline. Any other questions? Okay. So last time we kind of finished up talking about catastrophic cancellation and how this could be bad for us. The homework that's released right now has some instances of where this could be problematic, so keep an eye out for it. We have lots of different ways to model these types of errors. They're very difficult to actually pinpoint exactly other than doing a calculation and knowing what the right answer is, so basically experimentally. But one way we can do it is saying, all right, so if I have a floating point representation of an operation in general, so again, that's this floating point business here. So the floating point representation of x, some operation y, we can model like I'm doing here, where we're saying we have exact representations of x and y. So the floating point operation itself is not dependent on that representation, because we know there's inaccuracies in that. In this case, we're actually saying, well, there's going to be some small error that's machine epsilon. So that's the delta part of this, plus the real answer. Okay? And right now, we're also actually modeling this x operation y as being also dependent on that, or the floating point error being dependent on that operation itself. Okay? So this is one particular choice. We went through some algebra here. We just literally multiplied everything out and found out that in the end, when we're actually calculating the relative error, because the relative error is really the thing of importance here, we found out that the relative error is about delta. So if delta was machine epsilon, which is oftentimes what we model this stuff as, for the addition operation, it's fine. Okay? It's going to be about as good as we can imagine. All right? So hopefully on the homework, you saw something that was machine epsilon that might have been indicative of something not getting any better. So think about things like that. We can also model this a different way. We can say, okay, say the operation itself is perfect. We can add two numbers perfectly together, but we have a representation problem. So the representation of x and y in a floating point numbering system is going to be flawed unless you're lucky and you choose the right number. Okay, so in general, we have this problem. If we do that type of modeling, we have x times its representation. And here we're also assuming that the floating point error is dependent on the value of x itself, again, which is often the case. So we're doing that. We say delta x, delta y. That's just an assumption. We can have them both differently. We do some algebra. We factor out x plus y, which was the original operation. And then we have this fraction. So again, this is what we, doing a little bit of algebra, find something called catastrophic cancellation. This is observable. We can show lots of different cases where this is the case. In fact, we're going to see a few more today. But the key is that when you come down to the relative error is going to be 1 over x plus y. So if 1 over x plus y is big, that means the error is big. The floating point error is going to be big. Okay? And this is just has to do with modeling the fact that the representation of these numbers is not exact. Okay? So there's lots of things here to just be aware of. The biggest thing here is that if you're doing two numbers that are possibly very large, or they're nearly identical to each other and they're opposite sign, or you're doing the subtraction operation, which would give you the exact same thing, you can be in trouble. Usually it takes a lot of steps. This isn't still necessarily a gigantic thing. It depends on what x plus y is, because we're still multiplying by delta x and delta y, which if those were machine epsilon, we still have a factor of machine epsilon in here. But x plus y being arbitrarily large, so machine epsilon is 10 to the negative 16th, if x plus y could be the largest numbers in our floating point double precision system, that's 10 to the 306th, much, much bigger than 10 to the negative 16th. So we still do have to worry about this as we go along. All right. So that was where we left off last week. So now we're going to go into a little bit more a detailed analysis of some of these things where we have kind of more interesting operations, not just addition, subtraction. Here we have the function 1 minus cosine x over x squared. Okay? So, and we're going to explore x within the range of negative 10 to the negative 4th to 10 to the negative 4th. Okay? We can do a little bit of math. Just take the limit of this thing as it goes to 0. And it's equal to 1/2. You do some L'Hopital's rule, and you get 1/2 back out. Okay? Now, you could say, well, you know, this could be hard, but we know from calculus that even though x squared, violating that at 0, it's not really a thing. But computationally, on our computers, if we actually don't do L'Hopital's rule, what happens? You could think, well, maybe this is going to be a problem. Okay? So we're going to get to that part. It is a problem, as you might suspect. But what about the floating point operation piece? So if we actually go through, let me open this up real quick here. I just compute this thing. There we go. We see something kind of unexpected. Okay, so at this point, I'm cheating a little bit. I'm using single precision floating point, but I'm definitely not getting 1/2 out. I'm getting 1 out. Okay, so that's a little odd. We don't expect that. In fact, there's even more interesting things going on if I go a little bit further away. This is a fairly well-behaved function, even away from 0. But we see all these interesting discontinuities and all sorts of weird stuff happening. So this is just due to floating point operation error. Okay? Now, I'm not actually going to do the calculation for exactly why this is happening or why this might be going on, because it's incredibly complicated. The actual evaluation of cosine itself is usually around 20 to 30 different operations itself. So weird things can happen very quickly, and we really have no control over it other than we know this might happen. Okay? So we can also play with this a little bit more. So here we see, well, the actual error, the relative error is actually getting up to 1, which is not great. If we go to double precision, so that's what we usually by default use, you can see this is actually going down to 10 to the negative 7th, which is much better. And it's, you know, there's some issues right at the origin, kind of what we'd expect there to be. But it's still not, it's not too bad. If we went back down to half precision, we just see a problem. Okay, so it's just kind of throwing up its hands. So we definitely have to be careful with these things. We can easily get order 1 type of errors, relative errors, very quickly in this type of stuff. Okay? So unfortunately, as this might suggest, unless you know the answer, it's hard to say, unless things are going crazy, that's a floating point error problem. So we're going to learn more and more about this. It's usually very case dependent. But if you're seeing weird things you're not expecting, always suspect floating point error might be an issue, especially for difficult things you might find. Okay. So this is another interesting example. So this is a big polynomial. It's relatively big. I mean, we can stick numbers in by hand and calculate this. Any calculator can do this, but maybe there's something to this. Maybe this is a little bit more difficult than it looks like. Polynomials are wonderfully smooth. This one happens to have an odd order, but that's fine too. From a theoretical standpoint, from an analytical standpoint, there's nothing wrong with this polynomial. But what happens if we actually evaluate this thing is we see something a little crazy. Okay? So it's not big. It's negative 0.25. Okay, so just to show you the code. Here I'm just calculating around 0, and we should be getting back something that looks like 0. Right, for this particular polynomial, it's basically 0 at the origin. So I'm just evaluating it using my normal NumPy functions and plotting it around it with just different types of floating point operations. So this is half precision, and you can see this is kind of oscillating around 0, but all the way up to 0.025. So that's pretty significant for a very smooth, nice function. This, of course, gets a little bit better as we increase the precision. And now you can't see anything because it's not so bad. If I actually get rid of the y limits, now you get to start to see what's going on. It goes a little crazy. Right? Now note that the actual magnitude of these fluctuations are small. They're getting smaller as we go down, but we're not exactly at 0. So can anybody actually theorize with your neighbor exactly why this particular polynomial is not a nice polynomial for us? Give you like a minute. Take a guess. There's something about that polynomial that actually is not great by design. Any guesses? What's wrong with this polynomial? Yeah.
Possibly the coefficients being multiple.
That is because I wanted something to happen. That is part of it, definitely. Any other guesses? Yeah.
So I think you were calculating the wrong one instead of.
Did I have the wrong polynomial up there?
So if you're calculating the wrong one, then.
Oh, I'm calculating the wrong one. Yeah, you're right. That's 0, but yeah.
So everything is wrong and
Yeah. So the fact that this is it's changing its sign on every coefficient is not great for us. That's not exactly it. It actually does have to do with the coefficients themselves. At 1, we expect this to exactly cancel out. But as we get close to it, then those powers are going to be an issue. right? If we're taking something as slightly not 1, in that representation of slightly not being 1, it's going to be amplified by those powers. And so then comes in the positives and negatives and the coefficients that are supposed to be exactly 0 if I add everything up. Okay? So by design, this is a difficult polynomial to deal with. And there's multiple ways, actually, that this polynomial is difficult. So we can actually go back up to double precision floating point, and you see it's down to 10 to the negative 14th at this point, and then it diverges from there because we don't expect it to be near 0, but we still see this kind of noise. So if you're starting to see, if you're doing a homework or something like that, and you see this type of stuff, it's more than likely a result of floating point something going on. This isn't necessarily concerning all the time. Sometimes that's what you expect. You've pushed your accuracy of your method down far enough that the error is going to be at machine precision, and we're close to that here, so we're not so concerned about it. A lot of times this type of error at 10 to the negative 14th, 15th, 16th, if we can get to that, it's about as good as we can do. We can't really do much better than that. Okay? So even for nice functions, or apparently nice functions, even though this wasn't not one of them, things can still go awry. Here's another problem. Oops. Come on, go down. Okay. So in this case, we have a function, two functions. We have little f and capital F. So what's the relationship between those two? X plus 1, the function f of x equal x plus 1, and that rational function. Analytically, they're identical. Right? We can remove that pole, or we can do a little bit of algebra. Now, as we saw before with the problem of the cosine, we know that analytically, we know that thing had to be 1/2, but we saw we had issues when we approached 0 because we weren't using any of that mathematics to inform what we're doing. So think about that case, and then think about this. We're going to compare the small f of x with this capital F of x on a computer. So what might go wrong? I mean, there's the fact that I'm going to be evaluating this around 1, right? And that's probably going to be problematic. But think, again, take a minute, discuss with your neighbor what might be going on with this, where you think this would go, and then we'll actually look at what's going to happen a little bit. And feel free, if you have the notes in front of you, to run it and think about it as well. Okay, so we have a problem. We're not so surprised by this. If I'm just going and I'm actually evaluating this thing around 1, 1 minus 1 is going to be 0, and I'm going to get a divide error. Because again, we're not actually giving the machine the ability to understand that actually shouldn't be there, that I could have done some algebra and gotten rid of it. So we can see that the error actually is not insignificant. It's 0.02. And this is the absolute error in this case. We can look at things like, if we go up to oops, not 132. That is the wrong number. This number decreases. Okay? Now, we saw this actually in the last case as well. The reason why this is actually changing, because we still have that problem at x equals 1. That hasn't changed. and hence why we're getting this invalid value encountered. Okay, that's actually just telling you found a divide by 0. The reason why we're actually getting a bit better of an answer in this case is that because we're using more precision in the floating point representations, we can actually get closer to 1 in that answer and do an operation. So 1 plus a little bit minus 1 still gives me back something that's non-zero. And because I have more bits to work with, it's giving me a better result. So if I go down to 64, or up to double precision, you can see this is getting back down to 10 to the negative 15th. Okay? So it actually is doing what you'd kind of expect. The error is maximally around 1. However, the closer we get, the better this ends up actually working out for us. Okay? Because it's still doing the division with enough precision that it's going to work. Right? Don't expect this always to happen. In fact, the reason why I'm showing you these examples is a really important thing to remember about computation in general is if you can algebraically make the problem simpler or safer, and whatever that means, do so. Do not rely on the computer to always give you the right answer. It can do all sorts of crazy things. Do not rely on double precision to always solve all your problems. So definitely, if you were trying to take a limit, evaluate a function, and you see some way to make it simpler, easier to evaluate, then do so. That's very important. Sometimes it's hard to know. Sometimes you kind of run up against it, like, oh my God, this thing is blowing up. I don't know why. Well, it turns out you could have done some algebra and simplified it. Okay? All right. Not to be outdone, let's add things together. So we're going to be generally addressing a combination of error. In particular, we're going to care about truncation error and floating point error. And they're going to overlap. And we're going to have to be able to tell the difference as best as possible. So just as a review, truncation error is really saying I have some, say a series, a Taylor series. I can't represent all, the infinity number of terms on that series. So I truncate that series at some point into a finite sum. And so there's some leftover bits that I'm not actually using in the approximation. Okay, so we're going to see a couple more examples of this. But sine of x is approximately equal to x minus x cubed over 3 factorial plus x to the 5th, 5 factorial, plus something that asymptotically looks like x to the 7th. Okay? So if x is small, near 0, which is where this is going to be centered at, that's where this Taylor approximation is centered at, 0, that means that it's going to be dependent on how close I am. And the rest of those terms are going to go as x to the 7th. So if x is really small, it's close to 0, then the rest of those terms are going to be maybe small enough I don't care about. Okay? So again, just trying to get a nice feeling for what we're going to be using these approximations for. Now we also have to worry about what if x is not representable exactly in floating point precision. I have some minus signs here. Is that concerning? Now we kind of throw up our hands and say, this is really complicated, so maybe we need to be careful. And how does this actually end up coming up? Well, the best thing to do is look at some examples. So here's an approximation to a derivative. And we're going to go through this in a little while, but suffice to say, this looks like the definition of a limit of a derivative. If delta x goes to 0, I'll put a limit on there. That's one of the definitions we like. So if delta x is finite, which would be representing some sort of approximation to that derivative, so this would be a tangent approximation or secant derivative, whatever you want to call it. Okay, well, we can look at this on a computer and see how good this approximation is, and vary delta x such that as delta x goes to 0, we can't get to 0, but we can get close to 0. How does the error behave? Okay, so here I've just specified f of x is equal to e to the x because, I don't know, why not do something simple? And then we're going to look at the x equals 1, so we're just going to approximate the derivative around there. And this is what happens. Okay, so here I have a little bit of code. This is another way. Some of you were wondering how to use log space. You don't have to use log space. You can do kind of linspace if you're careful. Here I'm also providing a list comprehension to do the same thing. Use whatever you're comfortable with. We're coming up with a set of points. So and then also the delta x for those points. I'm approximating a couple different derivatives here. So this is the one that I had before, and I'm just plugging in e into this. So that's this approximation here. And I'm doing another one, which is a centered derivative approximation. So that would be the secant approximation, just to see what happens. And I'm going to plot this. So here we are. I see some interesting things. Okay, so what do you think is going on? So just to kind of explain this plot a little bit, delta x is getting smaller from right to left. So this is a worse approximation, we think. It's 10 to the negative 1. This is 10 to the negative 16. Oh, I can't even see that there. 10 to the negative 16. Okay? So from an analytical standpoint, we expect as delta x goes to 0 that the approximation gets better. And then I'm plotting the absolute error on the y-axis. Okay? And I see different behaviors for each of these different approximations. Okay, so the one-sided difference, that's the first one I showed you. That's the blue dots, and the centered ones are the orange dots. Okay? So again, take about a minute, discuss with your neighbor what's going on. And why is this important to us? Oh, sure. That good? So any guesses to what's going on here? So I'm not changing precision at all with this calculation. I'm leaving it at, actually I'm not even changing it. This is double precision. I'm seeing this. It gets worse if I'm not using double precision, which should actually be a good indicator what might be going on. So given the topic of the class right now, of combined errors, what do you think is changing? Why is there this inflection point? What's happening to the numbers I'm using? Yeah, so what's happening is that as I choose a smaller and smaller delta x, those numbers are actually getting closer to each other. So eventually, what's happening is I'm using a better approximation for this side of things, and it's actually getting, the error itself is getting smaller and smaller, and then all of a sudden, floating point error takes over. So here, the way to read this is that truncation error, so the error in the approximation is dominating the floating point error up until this point, and then all of a sudden, floating point error actually is adding so much error to it that it's actually overwhelming the accuracy of the computation. We'll go into why exactly there's a difference. Why is this point over here? This point's over here. There's a mathematical reason for that. But this hopefully will suggest that using a better and better, more accurate approximation from a truncation error standpoint doesn't always give you a better answer. Eventually, floating point error can overtake your answers. So this is a particular example that combines them really, really effectively to be bad. That's really what's going on here. We're subtracting two numbers that are going to be closer and closer to each other and seeing how catastrophic cancellation ends up kind of coming back to haunt us. If we had other operations, like we saw in the first homework, if you did the sums and things like that, you see that the thing bottoms out and then becomes flat at 10 to the negative 16th, but the error doesn't go back above where it ends up at. So sometimes this happens where the floating point error actually will increase and dominate the error. Sometimes it just stays flat. You can't get any better than machine precision for these types of things. It definitely depends on what's going on at the time, what the operation you're trying to do is. Okay, well, we've been talking about Taylor series, so why not take a Taylor series and consider that? So here's a little bit of a different question, though. What we want to do is pick a finite capital N, where capital N is defining the point that I'm truncating the series at. This is a series for e to the x. I'm given a range, a to b. And the question is, can I find a value that will give me an error less than 8 times machine epsilon? So how might I do that? Well, there's lots of different ways to do this. You can actually make estimates to this. It is non-trivial because you have to have some operation. You have a big polynomial that you have to know what the general term is, which we know now, but you have to also know how these numbers are changing. If A and B have both positive and negative pieces of the interval, the real line, we could get into trouble, we know, because it's going to become an oscillating series. Right? That polynomial actually might change sign depending on little n, the term of the series. If it's strictly positive, we also might be okay. If it's strictly negative, we actually probably aren't okay again. So we have to be very careful about these types of things. But we can do all sorts of stuff, not a least of which is just calculating it. So here I have an exponential function. It's going to be calculating it using this series approximation. And I give it the x point that I want to evaluate it at and the number of terms. And it just adds up the terms in the series. Here, this is a little bit of a funny thing. If you want to get the factorial function, you have to use scipy, which I haven't really talked about much. The factorial is actually a special function, or it's considered a special function, especially if you can evaluate it at things other than integers, which is why it's in the special function set. But that's basically just implementing this thing here. And if I want to, I can just brute force this and just check to see when does this thing end up being less than, the error being less than 8 times floating point precision, which is exactly this check here. Okay, so floating point precision, 8 times that. And then the error, I'm calculating the error here. So I guess this is the relative error. Yeah, that's what it's. And I'm just checking 1 through 50 just to see what happens. And we can print this out so you can see what's going on here. And we can kind of see, it's decreasing around x. So I'm actually allowing x to vary. Usually you just pick an x so that you know that. So in this case, I am actually kind of doing the harder problem with having -2 to 2. And I am using double precision here. So, excuse me, single precision. So the fact that this is around 10 to the negative 7th, which is machine precision, machine epsilon for single precision, this is doing pretty well. We're actually seeing something that's going to give me a good approximation. We probably would want to increase the number of n's here. If we actually do this to 64, you can see that the actual error goes down to 10 to the negative 15th. But the key here, though, interestingly enough, is that the number of terms in the series I need to get a certain precision or a certain error precision goes down, not up. Okay? So what's really saying here is that the floating point error actually, even though we have a truncation error going on here, the floating point error was also being difficult. So it's very non-straightforward to do a lot of this stuff. Just realize when you start seeing things, you're dealing with numbers that are near 10 to the negative 15th, and 10 to the negative 16th in general, weird stuff is going to happen. And we'll get more comfortable with it as we go on, but just recognize that could happen. Okay. so here's, this is slightly existential. But so the relative error. We've been using the relative error to calculate things, but should we even trust that? The relative error is a calculation that could have two numbers that are very close to each other, and we're subtracting them. Well, okay, so let's go with that. Here are two identical algebraic relationships. All right, x minus y divided by x. You could do this with y too as the normalization, and 1 minus y over x. Okay, so this is, I don't know. Obviously, I'm showing you the example because it's going to be mysteriously wrong. But which way would you actually want to go? You can use either one. We clearly are using the top one for a particular reason. But maybe we can analyze this. So let's actually look at that a little bit. So we have the error for the first one, which is x minus y over x. So this is slightly weird because we're going to compare the true thing to the fake thing and subtract the two. But we have floating point error. We're going to say that this is really a combination of the division operation and the subtraction operation separately. Now, that's an assumption. They're going to feed into each other. So here we're saying we're going to do the subtraction first because, of course, that's our order of operations, and then we do the division. Okay? So I model this not with the loss of precision due to representation of the numbers at this point, just actually the operation itself. You can do the other one if you'd like. So we have 1 plus delta plus, and then the delta associated with the division. And I do a little bit more algebra, and I get basically the multiplication of these two things as a polynomial times the original thing I wanted to get out, so the relative error. Okay. Doing it this other way, I'm going to divide y into x parts. Okay? So no, really what's going on here is I'm switching the order of operations, and that's what's actually going to be different between these two. Then I'm going to do a subtraction. Now the subtraction is normalized to 1, right? So maybe that's a little bit nicer, but we're going to assume one's going to be done before the other because we have to. We do some algebra. We assume that it's the operation that's introducing the floating point error. So we're again associating the division, delta divide thing, and now we're doing delta minus. So the operation we're actually performing has changed slightly. Okay, so now what happens? We're going to make an assumption. So in general, not every operation has the same floating point error. Division is a lot harder to do than addition or subtraction for that matter. At this point, we're going to say they're all, because we're guaranteed that they're all below machine precision, we're going to say machine precision is going to define delta for us. So all the deltas in our problem are going to become epsilon. And then we're going to look at the differences between these things. Okay, so we have the original definition. So we have the error minus E1 divided by E. So this is another relative error, except we're doing it in exact arithmetic. Okay, so there's no floating point operations. We've already taken care of that part. So if I go around, we know we want this. This is the actual definition of floating point, or excuse me, of relative error. Gotta say that. And then I'm going to calculate the relative error with what we just did from a floating point perspective, which was this piece here. So it's this, not that bottom. This thing here is our approximation and floating point, divided by the true solution. And we can bound this actually nicely by replacing the deltas with epsilons and collecting like terms. And we see you have 2 epsilon plus epsilon squared. Okay, so that's just doing a little bit of math, canceling out everything where needed. And we see, well, 2 times epsilon, but still epsilon. So if that's machine precision, we kind of just assume we can't do any better than that anyways. Plus epsilon squared, which is even smaller. So we're quite fine with epsilon squared as well. So we're finding that, well, this isn't so bad. I've done 2 operations, and it seems like the worst I'm going to do is maybe double machine precision, which generally we don't care about. Constants out in front of those things. Okay, so this works fine. There is an error, right? We're actually comparing the floating point operations to the real solution we want, but it seems to be a fine thing to do. Of course, we go to the second one. So this is the 1 minus y over x piece. So if we go over here and we plug in a representation for this, we do a little bit of algebra again. Note that I'm actually keeping little e. Little e is the exact solution to the relative error. I'm keeping it around because it's a little bit more compact because I am representing it differently. But at this point, we could actually use either algebraic form that we had before. Right? It's only the floating point operations, the floating point approximation that I'm showing that's going to be different. So you go through all the algebra here and manipulate it in such a way, and I find that there's a bound. Okay? So that bound is machine epsilon plus machine epsilon squared times something else, though, this time. And that's usually a bad sign. If 1 minus e over e, if that ends up being large, which it could be, this is kind of arbitrary, we can be in trouble. All right? Now, the key here is if what we really want to know is if the relative error is going to 0, then we have a problem. All right? Because now I'm doing 1 minus 0, which is fine, divided by 0, or something very, very close to 0, and now that thing is blowing up uncontrollably. Okay? So this particular form of the relative error is no good for floating point precision. Okay? So this is actually starting to get into the idea that we're only dealing with operations here. We're not dealing with representations of numbers. But that order of operations that we kind of switched around mattered. This is why we state things like floating point precision or floating point arithmetic is not commutative. I can't change things. Can't multiply, divide, change the order of operations, even if it's completely fine if you're doing it by hand or analytically. Okay? So this is a really good example of that. We can also show this actually directly via a calculation. I should mention this is actually a blog post by Nick Hyam. He's a applied mathematician in Britain, likes to do things with matrices, matrix function evaluations. So this type of stuff he is quite knowledgeable about. So we're just basically actually calculating exactly this thing. Now I've added a lot more here. You can see that the divide that I'm requiring is going to be to a certain precision. And that's because I wanted to actually explicitly say this division is being done in single precision arithmetic. Otherwise, NumPy gets a little too smart for its britches for my purposes and actually fixes this for you. And actually is smart enough to know what precision to use and get around it, which is always unfortunate when you're trying to show that things break. So here we go. We have a comparison of the relative error. So in single precision, we see the x minus y over x. So the kind of the one that it's the canonical definition is all below 10 to the negative 7th. So it's actually doing about as good as we can do. We know that that's going to be about epsilon. So actually that estimate we had seems to have guessed it pretty well. On the other hand, our other representation is getting pretty big. It's not so big, but it's 10 to the negative 3rd almost. So there's more error here. Again, it depends on what the actual relative error is going to be looking like. This type of stuff. We can actually if I actually do 64, I don't know if this is actually going to work. Let's do 16, because that one I think is a little bit more obvious. Did I miss any? So note I'm cheating here a little bit. Because I'm on a machine, I have to calculate something. I'm still using finite precision arithmetic to calculate the true answer. So that's why I'm not going to show you double precision, because double precision is going to be exact, and that's cheating. But I can show you single and half precisions, because that's actually going to be more realistic. And here we see even more entertaining plot, where it's a mess, right? And could you actually come up with why it's doing exactly this? Maybe. I don't know. I have no idea, honestly. it's complicated at this point. So we just have to be careful with things like this. I don't actually know where the blue dots are. Oh, did I? Should be 16 everywhere. This one's fine. That's the exact. Oh, here it is. You're right. Thank you. Oh, there we go. So in this case, we actually see neither of them very good. And that's mainly because we're using half precision at this point. Okay? By the way, if you do see me make a mistake, do not wait until I'm sitting here looking silly, trying to figure out why my program's not working. Just let me know, because inevitably I'm going to try coding in front of you, and coding in front of a bunch of people, it doesn't always go as planned. And since there's a lot of you in the room, at least one of you will probably figure out what I typed wrong. So keep your eyes peeled, as I will make mistakes from time to time. Okay, so that actually does wrap up our discussion of floating point error and truncation error, how they come together. The last thing I would like to point out is that there are a lot of resources on this. This was mostly for your edification. If you want to know more about this, these 3 links are great. If you want to understand floating point calculations a little bit more carefully than what I've demonstrated, that calculator is kind of entertaining. And there's books about this entire subject, one by Nick Hyam, actually. So feel free to peruse this. Now, that being said, this is not going to be something that I'm going to emphasize in this class, this floating point error business, other than it exists, and we want to be able to recognize it. Beyond that, like how you do these floating point things is going to be somewhat minimized past our discussion today, and then also one question on the homework. Okay? So be aware of that. If you have questions about it, please raise them in office hours and things like that. So, are there any questions on this particular topic? All right, ever onward. So another computer science complexity theory type of thing. This is going to actually be a little bit more important for us. So the reason why is because if we just have the question in front of us, like I want to compute something, and you say, well, why don't I want the most accurate thing possible? All right? Well, why wouldn't you want that? You want the best answer possible. Well, at some point, you don't want to wait forever. All right? At some point, you can only split up an interval into so many pieces. You could also use the highest precision possible. And it seems odd that really we don't have computer chips that can go beyond double precision, at least on hardware. We can emulate higher precision, but no effort has been done to make it higher. Okay, so why is that? Well, it's because every single time we do an operation, that takes time. It takes one or many clock cycles on a computer. And so we kind of actually want to know what the magnitude of the effort that we're spending to do a certain calculation. So one easy way to think about this is I have a Taylor series. If I use terms all the way out to 10, that's a good approximation. Terms up to 100 is a better approximation, but now I've increased the amount of stuff I'm doing by a factor of 10. Okay? So if it was a hard series to evaluate, and it took me 10 minutes to evaluate 10 terms, then multiplying that 10 minutes by 10 means I'm waiting around for over an hour, and I'm personally a slightly impatient person. So this is why we're talking about this. We want to understand exactly how much effort it's going to take to do this in light of the fact that I also want the best answer possible. Okay, so I'm going to lead you through most of this. I want you to get some intuitive feel for how to do this, though. And the best way to do it is just show a bunch of examples. Okay, so the first one here, with your neighbor, think about this question. How many operations is it going to take to compute the matrix A times the vector x? And we're going to assume everything's nice. It's an n by n matrix, and it's going to be an n-dimensional vector, n-length vector. And then I also want to know maybe how many operations it's going to take to multiply 2 matrices. Okay? So think about those definitions and try to think about how each of these computations is going to be dependent on capital N. So capital N is the major parameter here. As capital N gets bigger, my problem gets bigger. So see if with your neighbor you can count and figure out how many of the operations these are both going to take. Okay, so AX, so matrix A times vector X is a little bit easier to see. And this also gives me an opportunity to talk about matrix vector multiplication and a very useful interpretation of such things. So matrix A has columns. All right? When I multiply a matrix A by a vector X, one way to look at this multiplication is that I'm going to get back out a vector, which is a linear combination of the columns of A, determined by the weights that are represented in the vector X. Okay? So if I have A, which has columns, those are my fake columns. All right, so this is A. And then X, okay, X1, X2, X, capital N. Matrix vector multiplication is basically each of these, what we're going to define as A1. Oh, I'm not leaving myself enough space. This is probably too low. 2, so that this would be nth column. So this is kind of standard notation. Sometimes we get the square brackets represent columns of A enumerated by the number below. Okay, so we have A1 through AN. We have scalars, X1 through XN. And so the multiplication here is going to be basically each of these columns weighted by each of the values of X. Oh, this is capital N. Okay. So the reason why this is actually kind of important, and what we'll see, is that this is often could be considered a projection. It's mapping the columns of A into some other space, like a column space, and things of that nature. So we're going to come back to this a few times a little bit later. But this actually is a good opportunity because this is also a way to actually decompose exactly how we do matrix vector multiplication. So this is clearly a sum. We have, say, I is equal to 1 to capital N of AI xi, like that, right? So something looks like that. And we can actually decompose this even further in the sense that I can add this as a sum, because in reality, each of these values, well, I'm not really being careful about this. Yeah, so we'll just leave it as this. So in this case, this is going to give me back a vector, right? Because this is still a vector. Vector times a scalar. Okay? That's not exactly right notationally. Bad on my part. The second thing here is actually going to give me a series of multiplications that's going to have to actually be in the right order. Okay? But the nice thing about this is we can start counting operations. So for instance, if we go down here, we say the vector A times the vector V. Okay? I end up getting each of the operations as I need it, and I can start to count the actual operations here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplications, 6 additions. Okay, so I'm always going to have a few more multiplications and additions. So where does that take us? Well, maybe we can't see the pattern. I mean, it's just one observation. So let's take it one step further. Let's look at n equals 4. We count 12 additions, 16 multiplications for a total of 28 operations. So we can generalize this to being capital N times capital N minus 1 multiplied together. And usually we're not, we can kind of, n squared, there are n squared multiplications, n times n minus 1 additions. So if we add those two things together, well, this is the dominant term. There's another n squared here minus an n. That's, insignificant compared to n squared. So we say that asymptotically the operation count is n squared. Okay? So that's how this kind of business goes. You can kind of see that this is probably the case just by looking at this double sum, right? I'm going from 1 to n again. That's a double for loop, which means I'm going to probably have about n squared operations. Okay? That's not exactly, there's additions being subtracted off, which is why we have this n times n minus 1 business. But it gives us about the right thing. So similarly, if I go to matrix-matrix products, you can define these as the product of two vectors, so the dot product between two vectors. And the vectors are going to be defined by the columns of A and B, being careful about that. We know that the product of two vectors is just the components of A times B multiplied together. So that's 3 times capital N operations just for the dot product. Okay? There are n squared entries in the resulting matrix, and since each of these entries is going to be a dot product, we're going to have asymptotically n cubed operations. Okay? So there's an implicit sum. If we basically replace our dot product in the top sum there, I already have two sums going from 1 to capital N, and I get another sum going from 1 to capital N to the final operation, and I get n cubed. Fascinating enough, although you'd think this is kind of like, how could you do any better? This is the definition of matrix vector products or matrix-matrix products. There are clever ways to do it faster. I find that completely mysterious. I mean, I know what the math is and why it works, but it's interesting to see how you can actually reduce this operation. In fact, there is a theory as to what the actual maximum reduction of this thing is. So here's another example. So we're going to evaluate a polynomial. So we've been doing this already, but the question here is, can we do it? Can we do it better? Okay. So we have a polynomial. There's lots of different ways to write a polynomial. Of course, we're going to see a bunch of ways in a couple weeks. But here we have a0 plus a1x plus a2x squared all the way up to a capital N x to the nth power. I can rewrite that going reverse order, which is unfortunately oftentimes what's done, so that P1 is in front of the highest power. It bugs me a little bit. But in any case, you can use either one of these, and we want to find the best way to calculate some arbitrary polynomial given some coefficients and an x value. Okay, so let's consider how we can rewrite this polynomial. So we can do, well, so first of all, we can just evaluate the polynomial directly. That's easy, we just write the thing. In fact, you can do this in a loop if you just have a vector of p coefficients. But we can also do something a little bit different, and that's nesting some of these things so that you basically are going to take out a similar power of x in this. So I get p1x plus p2. So p1 is multiplying this x cubed business. It has the highest power on it. So if I actually multiply through by this, I get p1x squared plus p2x, and I finally get the linear term. I get the right thing back out. So you can always do this for arbitrary polynomials. You may skip some powers, but this always works. All right, so question is, why would you want to do something silly like this? Well, so it actually is more efficient to do the bottom one, just from an operation count. Because when we're actually grouping terms like this, we actually are saving multiple operations. Okay, so let's see how this works. So here, just for the kind of naive, straightforward approach, we have p1 times x times x times x. I said 3. So p1 times x cubed. Okay? So you could argue that the power operation should be a single operation. It depends on the implementation. Oftentimes it's not, unfortunately. It's at least as expensive, or it could be the most expensive is just multiplying this thing out, and oftentimes that's actually how it is implemented, unless you have some special powers. We're not going to go into that. Let's just model it this way in this particular case. So we have the cubic term, and then the quadratic term, p2 times x, p3 times x, and then p4. Okay? So we can count this up. We have three operations to multiply the first term, and then an addition. So that's 4. Or I actually just keep them separate right now. So 3, and then we have 2 multiplication operations and 1 multiplication operation. So that's taking care of all the terms of each of the terms. Well, taking care of all the multiplication terms. And then we have additions between each of these things. Okay, so we can count this up. So this is a nice way to actually think about this. This will come up a couple other times. But we can actually look at this as saying, all right, well, if I put this largest term over here on the bottom of this pyramid, I know that this is going to decrease by 1 each time. So if I have an n-term polynomial, that first one is going to be n multiplications. All right? And it's going to decrease until I get all the way up to here and I have no multiplication. So this would be the constant term. Addition is not being considered in here for right now because we have basically way less additions. We have 1 addition for each term, so that's going to be n. But if we look at this, well, that looks like a triangle. And in fact, that's a good way to estimate this. It's a triangle that's defined by an n on one side and n by the other side, so we get n squared over 2. And in reality, the 2 doesn't matter. We can divide by 2, that's fine. But asymptotically speaking, this is an n squared algorithm. So let's go over here. So here's the simple example of a P3. So we have 1 multiplication and 1 addition in that first one. Okay? And then 1 multiplication and 1 addition, and 1 multiplication and 1 addition. So we've actually, because we're computing each of the multiplications all together as we go, and then combining the numbers, so I'm not actually going to be doing multiple multiplications. Basically, I know what x squared is. I can figure out what x cubed is by using the answer for x squared. So that's the redundant amount of effort I'm doing. Okay? So I can actually reduce this to order n. Again, there's an, well, actually in this case, it's 2n because I'm doing 2 operations for each term. But that, again, is immaterial. We get an n operations per polynomial. So again, algebraically, we just manipulate this thing into something that's a little bit easier to deal with, and we can actually get an order of magnitude difference. Now, the question is n big? Does it matter? Well, obviously, the bigger n gets, the worse this is going to be. If I have an n algorithm, order n algorithm, and I have 100 terms to evaluate, I have to do 100 operations. If I have n squared, well, that's starting to become a little bit more tricky. Right? We're actually going to be doing a lot more operations. So generally, we're going to be trying to find different algorithms that are going to reduce that power on that capital N as much as possible, because that's going to save us a lot of time. OK. So the last bit of class here. With your neighbor or with yourself, whatever you want to do, try to implement Horner's method. So this should be a for loop. Here's how I'm actually prescribing it. I'm counting from 0 just because it's what Python does. And I'm counting up, and I want you to evaluate this polynomial. So given the polynomial coefficients p and a value x. And x actually could be a vector if you want to make it that way. Well, I guess I'm just demanding it's a float here. You could make it a vector. That's fine. So the idea is to implement this. Okay? You can implement it both ways, and actually we could do timings of this thing and see that Horner's method is faster. We're not going to worry about that too much right now. Okay? So I'll give you a couple minutes about that. I'll show you how it's done, and then we'll wrap up our discussion. Actually. Okay, so real quick here. There's actually two different answers I'm providing here. One is the scalar version, so that would just be x is a floating point number, just a scalar floating point. And there is a vectorized version down here. It's a little bit more complicated. But let's actually walk through this. And I'll pretend that's not down there. So basically, what we're going to do, and I'm using y as the return. So this would be capital P. It's just capital P and little p look dangerously similar. So just to avoid confusion, what we're going to do is, oops, let me get back here. I'm going to start with P0. So this is going to be a slightly recursive thing, which is kind of what Horner's method is meant to be. You start from the inner part, and then you just keep on building and building with answers. So the first thing is going to be that first coefficient, P0. And then I'm going to do a for loop, like that. So this for loop is going to be taking everything but P0 onto the ends, and I'm going to stick each of the values of P into a variable called coefficient. Okay, so I'm just picking one off, one after another, and what I'm going to calculate here is that inner part of Horner's method. So it's this thing here, so I'm calculating each of these pieces at a time. And the nice thing here is if I start with y is equal to P0, it naturally actually gives me each of those things as I go. Okay, so actually this is done. This is Horner's method. Hopefully it works, actually. So the other way to do it is in a vectorized version. So this would actually be if it had, you really wanted x to be like -1 to 1, it's a Lin space vector or whatever. This is actually usually what we're going to be interested in. In this case, we actually have to evaluate a bunch of polynomials at the same time. Right? We have basically whatever the size of x is to do. So one way showing here is to just create a y that's actually just ones, and it's the same shape as x. That's what that beginning of that command means. And then I multiply it by P0, because they all start out with P0, regardless of what x is. Okay, so the x thing is actually going to be the thing that's changing. It's going in each of the values of y. So now y is a vector. And then it's the same exact algorithm past that. So y times x, y is now a vector, x is a vector, and I'm adding the coefficient, which is a scalar, but it knows how to do that. Because I'm always adding the same coefficient to every element of the vector y. Okay? So there's other ways to write this a little bit more cleanly, but we can see if we kind of have arbitrary coefficients in our polynomial here, we evaluate it, we create an x, which is in this case -10 to 10, just picking 100 is the number of points, and then I can plot this using my eval poly function here, and I get out something that looks like polynomial again. Okay. So we are actually out of time, exactly the right time. Thursday, we will start with root finding and optimization, an introduction to it. So I will see you Thursday, and have a good intervening time. Stay dry.